All right, today we're going to pull back the curtain on the world around us. We're going to explore the hidden internal forces that are in a constant state of war inside of, well, everything, and how they keep our world from falling apart.
You ever look at a giant bridge or a skyscraper and just wonder what's really stopping it from collapsing? The answer isn't just the concrete and steel you can see. Nope, it's an invisible battle happening inside every single material all the time.
So, let's dive into these invisible forces. I'm talking about everything from the tiniest bearing in a machine to the massive foundations of a building. Every object you can think of is constantly managing these internal pressures just to stay in one piece.
Okay, so here's the fundamental rule. Whenever you apply an external force, what engineers call a load, the material itself literally fights back. It develops its own internal forces to resist that change, and in the process, it deforms, even if it's just by a microscopic amount you never ever see.
Now, to really understand this internal battle, we need to meet the two main characters in this whole story, stress and strain. You can think of them as a cause and effect duo, and they are at the absolute heart of all structural engineering. First up, we have stress.
Imagine a game of tug-of-war. Stress is not the people pulling on the rope. No, stress is the tension inside the rope. It's the force distributed through every single fiber as they fight to keep from snapping. It's the material's internal resistance.
So, if stress is that tension inside the rope, then strain is how much the rope actually stretches. It's that simple. Strain is the physical result of stress. It's the measurable change in shape, the deformation, that happens when a material is put under a load.
And this relationship right here is absolutely crucial. Stress is the cause, that internal pressure. Strain is the effect, the physical deformation. You literally cannot have one without the other. They are two sides of the same coin when you're analyzing how any material is going to behave.
So if these forces are invisible, how on earth do engineers design for them? Well, they have some pretty clever ways of making the invisible visible. And they do it by systematically testing a material's limits.
The process is really methodical. First, engineers take a sample of the material and apply a very specific controlled force. They'll pull it, push it, or twist it. As they're doing this, they use incredibly sensitive instruments to measure exactly how it deforms. Then, they analyze all that data to basically create a unique stress-strain signature for that material. And the engineer's toolbox is pretty amazing. We're talking about everything from giant machines that physically pull materials apart to tiny little electronic strain gauges that can detect microscopic changes. They even use powerful computer simulations to model the behavior of an entire structure before it's even built. Of course, the whole point of all this testing is to find the limit, because every material can only handle so much. So, what happens when that internal stress becomes just too much for the material to bear? That limit is called its load-bearing capacity. It's the absolute maximum stress a material can take before something goes very, very wrong. For an engineer, knowing this number isn't just important, it's everything. It is the line in the sand between a safe structure and a catastrophic failure.
To make this real for you, here's a number from an actual analysis of a specific component. Engineers figured out that the maximum stress it could handle right before it failed was a massive 337.5 megapascals. To put that in perspective, that's over 3,000 times the atmospheric pressure around you. Knowing that exact number is what makes a design safe.
And when that limit is passed, failure isn't always just a simple snap. Oh no, materials can fail in all sorts of ways. They can develop cracks, they can buckle under pressure, or they can permanently bend out of shape. That's called yielding. They can even get weaker over time from repeated stress, which we call fatigue.
This all brings us to the real point of this analysis. See, understanding stress and strain isn't just some academic exercise. It's the absolute foundation for how we build a safe, reliable, and innovative world.
This is a perfect example of why picking the right material is so critical. For the exact same part, under the same load, a chromium alloy experiences higher stress and deforms more. A tungsten alloy, on the other hand, is way more resistant. Making the right choice there can be the difference between success and total failure.
And this science is absolutely everywhere you look. It's in the bearings that allow wheels to spin, the composite materials in airplanes, the joints holding bridges together, and even in the medical implants inside the human body. Every single one of them relies on a deep understanding of stress and strain.
So, here's the crucial point, the main takeaway.
By making these invisible forces visible through all this testing and analysis, engineers can design things that don't just work. They can design things that work predictably, reliably, and above all, safely, even when they're pushed to their limits.
And that leaves us with a final thought. As you're sitting there right now, just consider the chair you're in, the floor beneath you, the building around you. Take a second to appreciate all those invisible forces, perfectly balanced, all working together to keep your world from falling apart.